Hey everybody, we're doing a drone. My name's Saray.
My name's Ronov.
My name is Juan.
My name's Kevin.
And let me see. So this is our table of contents. Boom.
Here's our project description. We basically built a lightweight drone built around an STM32 microcontroller that is powered by a 3S LiPo battery, a BMP280, and a BN085 IMU. The system controls a small motor to generate lift and will perform a simple autonomous test where the drone lifts off and then descends. The design focuses on a basic motor controller and sensor integration. We used a quad chassis. They gave us a frame for mounting all of the hardware and a buck converter to regulate the power. Additional sensors are a BMP280 to estimate the altitude and a BN085 for motion tracking. And here's our materials. First off, we start off with the 3S LiPo battery, which is the main power source for the drone. Then we use the PMP280 to help the drone hold a stable altitude. Then there's a BN085, which is our IMU. It's our accelerometer and our gyroscope. It checks the orientation and the movement of the drone. And then here's our buck converter. It steps on the voltage from 12 volts to 5.9 volts. And then our ESS or ECS, electronic speed controller, it converts the flight control signals into motor speed. Our chassis, it's the frame that holds everything together. And then our breadboard, just a prototype board for connecting components before while we figure out the soldering. And then we use a brushless motor and a flashlight controller for the transmitter and the receiving system. And here's our FSM diagram. It starts off by powering on, which starts with the microcontroller, initializes the hardware such as the GPIO pins and the sensors, and make sure everything is responding. Next is our setup. It calibrates the sensors and sets the initial values and then waits until readings are stable. And then it goes on to accelerate. It spins motor slowly, and then it will start the initial lift. After it does that, it goes to increase throttle, which increases the motor speed, lifts off the ground, and monitors the altitude. Next, it will hover, keeps the altitude constant, but also use the sensor feedback to stay level and constantly adjust the motors. Once it does that, it raises the throttle. It slowly decreases the motor speed, lowers the altitude, and will also keep balance while going down. Next, after that, it will end, which stops all the motors, shuts down flight control logic. And once it does that, it'll reset, and then it'll wait for the signal to power on again.
So these are our test cases one and two. Our test case number one was the power system, which are which was done by Kevin. He tested if the battery and the regulator output was correct, and also he also tested for the if the system turned on. Our test case number two was done by Ranov, which was the STM32 controller. He tested it for if the program ran well, and he also verified if the PWM signals were generated. Test cases number three and four. Test case number three was uh, done by Juan, that's myself. Uh, uh, we did the IMU, which the testing was to verify the I score C and also confirming if the sensor data changes with the movement. And test case number four was done by Saray, which was the motors and the lift test. And he tested if the motors were spinning correctly and if the drone lifted off from the ground. And he also tested if the motor stopped after the drone stopped on the ground.
So this is what we have working and not what's not working right now. So actively right now, we are able to receive gyro data, altitude data. We have our controller connected to the mic to everything. The PID controls do work. Our differential motor speed does work, and our low pass filter, voltage regulation, I score C, UR, and PWM do work, which means we do have a minimum viable product. The only two things that we weren't able to completely get working was the raw gyro data printing for some reason, and we weren't able to test fly or hover the drone because it is still on a breadboard and we weren't able to solder it completely.
And our bus protocol, which was the I square C, the inter-integrated circuits, Uh, it was used as a data bus for data from the IMU and the altimeter, uh, and it was connected to the STM32. And we also used the UART, which was for transmitting and also receiving for the controller. And it was also for data transfer from the microcontroller to the laptop and for testing of data and PID control.
So this is the low pass filter. So we use the low pass filter to filter out noisy IMU and altitude data. So essentially what we use it to reduce the high frequency noise from our sensor data. And the way that we implemented it, any large jumps in the data would be blended into the previously filtered data, allowing for any regular regulated jumps that are small and not too large to keep flowing through at higher speeds. But any large jumps would allow it to smooth out the curve between where it is and where it thinks it needs to go. And we used alpha values of zero point 0.2 for our roll, pitch, and yaw, and 0.10 for our altitude. And we used pulse width modulation, or PWM, to control the speeds of our motors. We basically changed the wavelength of our ones and zeros, allowing by changing the lengths of the ones to tell the ESCs how fast or slow this motors needed to move. Our arm value and zero speed value was at 1050 milliseconds, and our max speed value is 1950 milliseconds. And anything in between, it is connected to a percentage value between it. And then we used timers 2, 3, and 17 to set up the pulse width modulation, and it was set to 50 hertz for all of them.
Okay, for PID is stand for proportional, integral, and differential control system, which communicate with STM32 and regulate the speed of the pellet to balance. So proportional change how much the upward status on the motor back to the target value using bias. On the error, we use percentage and frequency to calculate linear RPM, which allow the server to move right on the position by reducing cumulative error. At integral, it's sum of the running total of the input over time and keep track of the past error. It removes persistent error like steady state offset with too much would cause overshoot and slowing settling. For the differential, which is the future error rate of change, which predict future error behavior, and that will anticipate and predict how much speed the motor will spin. We will use altimeter as gyro to calibrate the speed. All of these interact with the UR to achieve precise control system environment. And this is an example from the MATLAB video I had to look at. Pretty much this is how we got our logic from, and that's its error. Let's say your drone is 50 feet in the air, it will have a 50 error, and then this again that will times it to achieve that same RPM. Conclusion.
In conclusion, we were able to build and test the drone, but there were still small things that we wanted to improve. We plan to solder everything on the PCB board and to make it cleaner and secure. We also wanted to add a camera so we could see where the drone was flying and also record the flights. Another improvement we also wanted to do was tuning the PID so the drone could hover better and also stay stable easier. We also plan to do to add a GPS module to track the drone while it is flying. And overall, there were still more upgrades and improvement we want to make in the future.
Okay, so this is part of the gyro testing. We simulate this using some software. And this is a motor PID testing.
This how off was
Speed increase. We'll do more back. Increase. Stabilize, go to hover. PID hover turned on. Hover goes back to stabilize. Speed increase. Speed decrease. Move left. Move right. Pitch forward.
And that's it, pretty much our presentation.